everyone, and welcome to this Zurich instrument webinar dedicated to SPM application. So today we'll focus on Kelvin probe force microscopy from frequency resolve to time resolve measurements. My name is Romain Stomp, and I'll be your host and presenter for the first part of this session, followed by Mehdi Alem. Both of us are application scientists with background in scanning probe microscopy and photonics respectively, and we love to show our instruments at work. So Mehdi is actually sitting in our headquarters in Zurich, so you'll see him later, along with our AFM setup while I'm sitting here in France. So therefore, the AFM microscope is controlled remotely, which I believe is quite a popular trend these days. And so hopefully all the transition will be smooth. Okay, so we have a very busy hour in front of us, and this webinar will be split into 3 parts. So we'll get started with the KPFM part, focusing on single pass techniques and how to apply this to amplitude and frequency modulation mode. So this section will take the bulk of our time, as we want to be as concrete and practical as possible with demo on a real setup. So this will then be followed by the presentation and demo from Mehdi on electrical pump probe method, therefore in a more time resolved approach. And we'll keep, of course, some time at the end for the Q&A session. So I'm actually very excited to present you this new content because so far we could only show how it works in principle, but we understand that sometimes the devil lies in the details, and so hopefully you'll get a better feel how this works. So for the purpose of this demonstration, so we'll use an MFLI for the KPFM part, along with the NanoSurf FlexAFM and a UHF-LI for the electrical pump probe, as you see here. So we love to work with third-party company to enable new modes and open up new possibilities. And so if you picked this NanoSurf microscope, it's because it's very compact, it's robust and easy to operate, and also because the train connection between Basel and Zurich is always on time. So please keep a lot of questions for us at the end. So you can write them anytime using the Q&A box at the bottom of the Zoom screen. And so we'll try to answer as many as possible today, and so provide answers by email to all remaining ones. So we will also share a blog post on these topics within the next 2 weeks after the webinar. So before we dive into the concrete stuff, let's situate Zurich instrument in the context of SPM application. And so let's start with this cloud view of the various SPM technique. So SPM comes with many flavors and modes of operation. And here's just an overview of the wealth of interaction and physics that can be probed with this. So ranging from high resolution topography in ultra high vacuum, and of course, everything related to scanning tunneling microscopy, to some piezoelectric response, some magnetically response and electrical optical sensitive techniques too. And the list could go on. So inside this blue square are the various tools and functionalities that are often essential in controlling the SPM setup and that are included in Zurich instrument product. So for the purpose of this webinar, we will focus essentially on electric mode, so EFM, KPFM, and of course time resolve SPM. And that will be a nice way to illustrate this multi-frequency lock-in technique, sideband analysis. Of course, we'll go through PID loops and data analysis in time, frequency, and acquisition. And at the end, so we will have this electrical pump probe method shown by Mehdi. So all these tools, you have them readily available with a few mouse clicks from a Lab1 user interface, as illustrated on this screenshot. And so the nice thing with Lab1 is that it can control multiple instruments, such as this MFLI, HF2LI, or UHF-LI, and can also easily interface with third-party setups thanks to its data server architecture and API or programming interface. So whenever you have optimized your measurement with a given instrument platform, but you need more bandwidth, more input or output, more time resolution, then you can switch to another platform without having to change from the comfort of the known user interface and program that you have already made. Okay, so, but how can we benefit from all these additional tools for SPM anyway? And so in a typical AFM experiment, so you'll start by shaking mechanically the piezo. You have some electrical drive. you can actuate magnetically the sample, or you can excite optically with some laser beam. And all this interaction then going to be sensed now by the tip sample force field. And that will give rise to rather complex tip trajectory in the time domain and complex frequency mixing and higher harmonic generation in the frequency domain. But at the end of the day, you only get the output from your photodetector, and that corresponds to a total force. And you are typically left with just a few observable for all these complex physics that you have, and which is assimilated as a resonator. So the cantilever can be seen as a mechanical amplifier, and so with a certain gain and bandwidth. But you can also demultiply this to more frequency, more eigenmodes, and so on. And so that's a nice thing also with lock-in, is that because you would have different actuation mechanism, they can all have their own reference. And now you can, for instance, link some of the mechanical reference that you have to some, let's say, some mechanical phase that you measure, and then to some mechanical response there. Or you can look at some as a magnetic actuation that maybe create some dissipative processes that you can link to some magnetic response. So for now, for the rest of this webinar, we will focus mostly on this electromechanical coupling, because this is at the heart of the Kelvin probe force microscopy. And so we will focus even more to like a single pass resonance technique, and I'll explain why. So basically by single pass, so we mean that we want to measure both the mechanical and the electrostatic force at once. So that's allowed to get closer to the surface, so for better lateral resolution. So you don't need to lift the tip, so you don't have a blurring effect, or like, let's say, rather longer range capacitive stray field. Of course, you go faster because you don't go twice on the same location. And actually, the most important is that you can nicely decouple the mechanical contribution to the electrostatic one. And this is actually very natural for the sensor, because it is already sensing all these forces at once. And so it's our job to distinguish, let's say, one that goes to a nice topography image and one that goes to a nice bias and showing the surface potential. But in order to do that, we need actually even more than lock-in. We need also an extra boost. And so this extra boost we get from this resonance amplification. So this resonance enhancement, so benefiting from this gain. So we don't want to sit, into the valley here. We want to go up the mountain at the top, because this is where you have the best signal to noise ratio eventually. This, of course, comes at the price, and that's the price of this known bandwidth. But outside of this, you can reject noise. Also, and that's something specific to lock-in amplifier, is that you can do some in phase and in quadrature, so basically at 0 and 90 degrees. So that provides us actually independent information on both axes, so for X and Y, and for amplitude and phase. Okay, so how do we apply this now to Kelvin probe? And so let's start with the mechanical loop. So it's actually rather boring. So you just have your favorite mechanical mode, whether it is tapping, so an AM technique. So if you have a low Q factor, or you're doing more complex stuff with a PLL, so a phase lock loop, if you have a high Q factor. But typically, so you only care about what's going on the first resonance. Then you will add some electrical modulation, and this will give rise to actually three terms. So a DC component that you will eventually need to compensate, and then F omega and a 2 omega component. And so so far, so the nice thing with amplitude KPFM is that the amplitude, the mechanical part and the electrical part can be independent, so they even can get their own resonance. So if you have picked the right frequency here for the second eigenmode. For the FM1, so there will be different variation, but let's start with this one. So we want to have some rather low frequency modulation frequency. Modulation frequency. And so when you start to have the mechanical shaking of your cantilever, and then you approach your surface, then the tip, of course, is going to send this electrostatic force. It's actually attractive, so it will shift to some negative shift, but that creates a detuning. It's going to create a detuning at this modulation frequency, and this gives rise to several sidebands within the bandwidth of this carrier. And now, very important between this FM and compared to the AM on top is that you have a phase relationship between the sidebands and the carrier. So it is a phase sensitive method. If you now look at some example, some real-world example, so you have you can use here 5 demodulators to look at all these frequency components, and if you sweep the DC bias or you have a feedback loop to compensate for the electrostatic force, you will eventually make this omega component vanish, and only the 2 omega component remains because this one is independent of the DC bias. So here's something worth to mention is that all these peaks will have to lie within this natural bandwidth of the resonator, and so that gives some constraints. So you can't just have arbitrary modulation frequency or much larger modulation frequency because this will actually decrease the signal strength. And if you have rather low modulation frequency, then you are limited by the demodulation speed because everything is counted over a small frequency span. So that's why there is also this so-called heterodyne FM-KPFM technique. So it's also a sideband, it's also phase sensitive technique. But that benefits from a different modulation frequency here. So instead of having the sidebands at F0 plus a low frequency modulation, you can replace this term by F1 minus F0. And if you put this here, then your new sideband is actually going to happen at F1. So now we are a little bit back to this example with the amplitude modulation, but we do it in a phase sensitive manner because this excitation is actually phase linked. I mean, it is coherent with the carrier here, which because of this excitation relationship here. And so in this case, we are sensitive to the phase. I actually recommend you to look at this nice paper from Amelie Axt, who is reviewing all these different methods and having some more example on heterodyne as well. So, and we will of course go through this during the demonstration. But why do we want to be sensitive to the phase anyway? Because it looks like more complicated. So everything else, so you need to be, you need some phase sensitivity and all that. And so let's look at, again, a very nice paper, so from Tino Wagner. And so we plot basically the force and the force gradient. So one is, so basically the AM mode will be sensitive to the force and the FM mode is sensitive to the force gradient. Both of them are have this parabolic behavior on the bias voltage, but one is sensitive to the capacitive gradient and the other one to the second derivative of the capacitive gradient. So if you now plot this contribution as a function of tip sample distance, and then you separate the contribution from the apex, the cone, and the cantilever separately. So first of all, you see that, of course, the contribution from the cantilever is rather boring. So it's always flat because basically you have 2 parallel plate capacitor, and then it doesn't depend much on the distance, and it's just a constant background. But now, if in addition you plot all of these 3 contributions with the relative contribution to the total force, you see that the cantilever itself has the strongest contribution to the overall force. And so you need to get quite close to the surface to really get some sensitivity from the actual tip apex. And even that doesn't get so much more than 40%. Actually, here I have to clarify that this solid line corresponds to a 5 nanometer tip amplitude. And now if you would go down to really small amplitude like 0.1 nanometer, then of course you also have more sensitivity from the apex. And on the other hand, if you go to higher tip swing, like 50 nanometer, then you're less sensitive. So that's for the AM part. And now if you look at the FM part, then first of all, we see that this cantilever contribution is actually much weaker to start. And when we actually get closer, this relative contribution almost disappear completely. and now we are mostly sensitive to the tip apex. So of course, this is actually very good news, because that means that we want to be sensitive to really what's at the end. And so that's the main motivation for doing all this force gradient and phase sensitive and frequency modulation technique. But of course, this also comes at a price, and the price to pay is that now you don't have this comfortable background force to feedback from. So you have overall a weaker signal to noise ratio, because of course the signal strength from the tip is much smaller than the overall signal strength from the whole cantilever, and so that makes the overall regulation a little bit more complicated. So with this in mind, so let's put everything together about how KPFM works on a complete AFM setup. So with the mechanical and the electrical loop. So here we have our force gradient applied between tip and sample. So we have a bias voltage. Here we can shake the mechanical piezo, and here we have the representation of our electrostatic or force gradient force, which follows this parabolic behavior here. And so we see that this electrostatic force will vanish for some value of DC bias voltage corresponding to this contact potential difference. And that's basically when the work function of the surface and the tip equilibrate. So that's why you want to eventually regulate on that. But first you will start with, of course, the mechanical loop. So in this case, let's say you have amplitude feedback to get the dissipation. You can have a phase feedback to have the frequency shift. If you would do a pure AM-KPFM, then the two loops can be independent. You don't have to care so much. You just have to measure now the electrical amplitude. But for FM techniques, then you want to be sensitive to the force, and this is carried with the frequency shift. So if you're doing this NCFM, or to the tapping frequency, to the mechanical phase of the tapping frequency. And so you have to feed this now into the demodulator, demodulating at this modulation frequency that at which you drive electrically. And then you have this X component from that tells you about the strength of the electrostatic interaction. And now you want to regulate this basically to 0, because of course now this probing voltage here, AC, so when you have strong force and you have a large X, and at 0, then you have, at the CPD, then you have a contribution at 0. So now, so basically everything happened between this probing voltage, AC here, and this DC compensation voltage here. And that's basically the root of Kelvin probe. Now this comes actually with also many different flavors, and we can't really go to all of them, but I just wanted to give you a bit of an overview. And also, I can't go into details about some dissipation KPFM, which is also very nice, but mostly for vacuum, because you need to operate in non-contact AFM. And I refer you to this nice paper from Yoichi Mihara and Peter Grüter on that topic. But in any case, you will always drive mechanically usually at the first eigenmode. And then you can pick some different frequencies, so either some rather low modulation or the first eigenmode. You could do it off resonance, but I think it has very little value because then you have no enhancement. And then or this difference of amplitude here. And now for this dissipation one, so that's why you need actually the PLL to log the phase, because then you can project the electrostatic contribution to the dissipation axis, and this is how you regulate or measure the electrostatic strength. So in terms of compensation, you always want to nullify, because that's when you reach the contact potential difference. So you want to nullify this electrostatic force by minimizing the X component dissipation, and as it is mentioned here. Just a few comments. So each mode can have actually some pros and cons. So in AM mode, the fact that we have this rather large cantilever background, so makes it overall fairly stable and easy to operate. It also allows to use usually smaller AC drive. So that's actually a way to reduce some artifact. And typically for in FM mode, because the signal to noise is usually smaller, than you need to drive higher. And then, as we mentioned, for heterodynes, the nice thing is that you are not now, you don't have many frequencies under the same resonance, so you can demodulate faster. And for these dissipation modes, you need both a phase lock loop and an automatic gain controller so that you can separate both axes. Okay, so now let's actually move to some serious stuff. And so let's illustrate how we connect our MFLI lock-in amplifier to this FlexAFM controller. So of course, you could also work with third-party microscope. And so the most important thing is to access some of these critical signals that you have here. So normally you would go via some breakout board or some signal access module or some direct connection to the microscope or to the controller. But at the end of the day, you want to get the vertical deflection. So basically the full the global force that you get and that is probed by the sensor. And for the electrostatic actuation, then you need to have some tip sample bias voltage. So one or the other on ground, or if you want to apply some additional offset, and you need to do it for both this probing voltage AC and this compensation voltage DC. Now, for FM mode, you need also to have the mechanical phase. So you use typically the shaker reference as an external reference input. And so whenever you have finished the regulation with the PID, or when the PID is on, then you can send out this contact potential difference value or the surface potential to the controller on an analog output so that it can also be imaged by the SPM controller. Actually, at the same time, you can also get the end of line trigger. So just a simple TTL at the end of every line, because of course, all these signals are also available internally. And then we can also image with the data acquisition module from the MFLI. So here you see that we can really separate the realm of the electrostatic feedback from the MFLI and everything related to the mechanical actuation, that feedback topography and imaging from the SPM controller. So as you see, I don't have a microscope here, so I control it remotely, and also we are not an SPM company. You know, Zurich Instrument is like digital signal processing and FPGA, and it's actually very nice that we can have one and do some, but we are far from ideal conditions. So we just operate in ambient condition. There is no vibration isolation, no acoustic enclosure. And I think just from this picture, you see that this is not an SPM company, but hopefully we still get some decent results. So for the point is to use also some commercially available samples and tip, because we want to keep it also as simple as possible. So we have selected here this interdigitated line array of gold and aluminum. So it's quite nice because it's different materials, so there are different work functions. You can actually even apply a bias to the sample between the gold and electrode. So that's also quite nice. But it's also fairly large area, so there is no small feature. And you have some grooves. So we found out that it's actually better suited for FM-KPFM. And then for the sensor itself, the most important, of course, is that it has to have good conductivity, whether it is fully metallic or well coated or doped. And so, and typical for sensitivity up to 40 Newton per meter works well. Of course, now if you have a coated cantilever, you have to pay great attention not to wear off the tip coating. And if you want to enhance even more this apex contribution, then high aspect ratio tips will help a lot. So hopefully now everything is clear how the demonstration is going to be conducted and how Kelvin probe modes work. So let me pause the presentation now and switch to the microscope. And I'll stop the video so that we can really focus on that. So the idea is to show how to interface with any third-party microscope to enable new SPM mode out of the box with a simple add-on such as the MFLI. So here we start with the user interface from the NanoSurf C3000 controller, as you can see here. So we have already approached and made, so we are doing it in dynamic force. So it's an amplitude modulation technique. So also mostly known as tapping mode because you are in ambient condition. In vacuum, you would rather use some frequency modulation scheme or non-contact AFM. And because you are doing, we want to be sensitive to the electrostatic force, you are using EFM cantilever and nicely conductive coated tip. We have already made some frequency sweep. So the actual resonance frequency is close to 74 kilohertz. And so from thermal fitting, we can also deduce the Q factor and the swing constant from here. So here we got already some initial images of the grid calibration grid samples that we mentioned earlier. So we have some alternative strips of gold and aluminum with some background oxide. So for the approach, we want to make it fairly soft. We can even have some bias voltage initially. And the idea is to have a fairly gentle tapping so that we don't wear off the tip coating. And at the same time, you also want to use not such a large AC drive because we want to limit the overall oscillation amplitude to 20 nanometer or less to remain within the same order of the decay length of the interaction for this electrostatic force. So here we do not apply any tip voltage from here because all the electrical loop is going to be controlled from the MFLI directly. So we can now switch to the user interface controlling the MFLI lock-in amplifier. Here is the Lab 1 user interface. So it is based on a data server architecture and the user interface is accessible from a web browser, as you see here. So let's go full screen. So that's the interface that controls the MFLI, but that would work as well for the HF2LI. So on the left-hand side, you see a bunch of modules that you can load. So here we have loaded most of the one that you will need for today. One of the most important one is the lock-in tab here. So on the left-hand side, you see the analog signal input from the ADC, and on the right-hand side, you see the analog signal output from the DAC. Both are sampled at 60 megasamples per second, and in between, you have the real-time digital signal processing. So with a few numerically controlled oscillators that can be distributed over 4 demodulators here. So every line corresponds to one lock-in, and which is own output. Well, now we want to actuate the cantilever electrically with an AC plus DC component. So here we have 1 volt at 479 kilohertz that is applied, and we also can add to the aux input 1 an additional DC offset that we generate on the aux output here. So here we have a plus 2 volt that is added to our 1 volt modulation. So with this, we can sweep the second eigenmode. So here we are using oscillator frequency 1 and looking at the demodulated amplitude from the lock-in. So here we are. So we have our first nice resonance frequency with corresponding fitting parameters. And just for the sake of argument, if you put here 0 volts, so there would be a much weaker electrostatic interaction, then of course the overall amplitude gets much smaller. So it's not 0 because it's not necessarily CPD, but it is definitely much smaller. So let's go back to 2 volt where we have good signal strength. And so with this, we can further optimize the signal. So let's first of all extract the important sensor characteristics like the resonance frequency, the bandwidth, and the Q factor. And so let's now optimize this value here and check that we indeed have a higher value, so more or less what we measured, and a stable phase. So since we notice that the amplitude has some dependence with the DC bias, so let's sweep this DC bias between -2 volt and 2 volt. So now instead of sweeping the oscillator frequency as we did before, let's sweep the aux output offset 1, which corresponds to our DC offset sensitivity. So, and measure the X and Y component. So here we have some nice response. So we see that X component is not yet compensated. We have some good strength on the X component, and here we have a linear dependence of the amplitude as a function of DC, which eventually drops to 0 when there is no more electrostatic interaction because we are the CPD. So let's do an auto phase and sweep again. And in this case, we see that Y is actually flat around 0, and then now all the signal strength is on X with a nice overlap with the R component. So we are interested in the amplitude dependence, but we can't use the amplitude directly inside the PID because the slope changes sign here. But the X component will work very nicely, and you can also calculate its slope. So it gains. So now we have a nice gain of 3.8 millivolts per volt, and that's what we can enter here into the PID. So something like this. And also the bandwidth that we have measured before. So this PID module, so we have 4 of them, and it's quite versatile because you can use many of the signal, demodulated signal as an input. So from any of the 4 demodulators that we have. So here we're interested in X1. And you want to act upon the aux output offset to compensate for the bias voltage. Of course, now the tricky part is how to optimize this PI value. And so that's why we are using this PID advisor, which will simulate the response according to some DUT model. So most of linear PID will have some low pass behavior in closed loop. So let's just use the first order one here. And so enter the gain and bandwidth that we have measured from our previous sweeps. We select a target bandwidth here of 100 Hertz, which corresponds to about 10 millisecond per pixel. And now we see the actual simulated response, or the step response on one hand, and we can also look at the baud plot, which is this low pass filter behavior with a certain cutoff frequency. And now our actual measured or simulated bandwidth rather is 122 Hertz for this PI value that we have that has been calculated. So let's send this to the PID, and so we are now ready to close the loop. So let's look at the DC bias now and the behavior when you close the loop. So as soon as I turn the PID on, I see that the value basically jumps to the CPD. So now the electrostatic is fully compensated. And if I even just make a small step, so just by adjusting here the bias, the set point, sorry, so you see that you have a rather nice step response from the PID controller, so rather sharp. So within the bandwidth that you have defined, of course, if you have you can go faster or slower than that, depending on the noise level that you want. But for our purpose, it will be quite good already. And so from the Math tab, we can also select the cursor area, which will provide us some additional information related to the signal to noise ratio. So, and in particular, so now we see that our CPD is actually at minus 240 millivolt, and that our standard deviation is 15 millivolt. So that's a good indicator for the signal to noise ratio. So we are ready to image, but first let's arm the DAC so that it will be ready when the scan engine starts. So we have defined a grid of 256 by 256. So that will be the size of our image in the nanoserve controller, but we can of course as well oversample here because we have enough demodulator stream. And here we also trigger from end of line so that we can record all the channels that we want. It could be much more than that, but let's focus on the CPD for today. So now that this is armed, we will also send the actual analog output of the PID to the BNC of aux output 3, and this will be imaged then into the nanoserve controller. So let's go back to this part. So let's resume the scan, make a nice image from bottom, and then look at some additional channel information, such as the CPD here. So the CPD has been configured from the signal access here, where we enable input B, and that's the one that the PNC that receives the signal from the PID output that I mentioned. So we just rename it CPD here, and that's what we display on this new image. So the topography is, of course, the same as before. We have the phase with only some feature on the edge. But of course, now we get more information from the CPD value, because even though the stripes look basically the same in the topography, in the CPD, we can clearly distinguish 3 levels. So one that would correspond to the gold stripe on the side, one that would correspond rather to the oxide here, and one that would correspond to the aluminum in the middle. At the same time, we can apply a sample bias, so between the gold and the aluminum electrode. So that's what we have actually done before. And so we can also see this effect now. So let me change this directly into the software here and look at it into the plotter. So in the plotter, so we can, so we basically have the same information, but just as a function of time. It's like unrolled. Let me get rid of this, and let me apply different sample bias between this gold and aluminum electrode. So here I'm starting with half a volt and with 1 volt. And just yeah, for the sake of consistency, let's just make sure that this is more or less what is applied. And so here we had our gold strips before and after applied about 500 millivolts. That's what you see here. And if I do it between here and here, I again have close to 500 millivolt. So that's consistent, and that's what we would expect. So if I return here, and that's what we see as well. So now this lighter area corresponds to a higher value of, well, now I went back to 0 actually. But this used to be 1 volt. And the nice thing is that whenever I'm changing a bias, even if it can be fairly abrupt, even if it's from 0 to 1 volt suddenly, you see that the topography just continue as is. It's totally unaffected. So there is no leakage or contribution of the electrostatic in the topography, so that we can be assured to measure the true height. So let's pause the scan now, return to the Lab 1 user interface, and now load a different configuration so that we can switch to this heterodyne mode. So for this is actually quite easy. So we can easily switch mode by simply loading a different file. So now the new layout and settings are being loaded. So we can switch more easily between new modes. So here for the heterodyne, so we see that we are locking now to the shaker, so to the mechanical phase of that tapping mode frequency. So coming from the shaker, from the controller. And we want to excite at F1 minus F0. So for this, we need to use this modulation option here. So where we can configure our sidebands to be equal to F1 minus F0. So and so we are doing this with the carrier minus the modulation, where this is 47.1 minus 74 kilohertz. So this gives us this 397 kilohertz that is applied again with 1 volt to demodulate to 3. So you also notice that the reference mode is not manual anymore, but it is controlled by the modulation option. And so with these 2 different frequencies, that's also why it is grayed out. Also, the PLL now is taking care for the mechanical tracking of that tapping mode frequency. So we are again at the second eigenmode frequency, and so we don't need to sweep it again. But on the other hand, we are interested in looking again at the behavior of the amplitude as a function of the DC bias. So we are applying the DC and looking at amplitude 1 as a function of DC. So this is also quite good. So we see that the phase had already been compensated because it was saved in the right settings. But in case you need to do it, you can't do it just from a simple auto phase. And the reason is because we are using this mod option. So we are so the phase would be between two different oscillators here, and also so that's why, because we want to change the phase of demodulator 1 by changing the drive on demodulator 3. So that's what we see here, and so if we change this value, of course, yeah, we see it right away, and so we have noticed that maybe this is a pretty good value for this frequency. So this is exactly what we got. So we had a nice stable phase where the Y component is flat, and then all the contribution is again on this X component. So we are a little bit back to square one, like we had before, except that we have this phase sensitivity. Overall, you see that the gain is weaker, and this is not so surprising because we are sensitive to the force gradient and not to the force only. So we do not have this background contribution from the cantilever anymore. So we are more sensitive to the tip contribution, but the overall signal is weaker. So with this, we can go again to the PID tab. So nothing changes on this side because we are still demodulating X1 and we are still acting on a DC bias voltage, except that we have a gain that is weaker on this order that we can simulate again with the advisor. So we get, of course, similar bandwidth, and then we can copy the value here. So let's look at the behavior when we close the loop. So again in the plotter, but maybe looking at this guy instead. So let's make it this way. So when I close the loop, I see that value jumps to CPD again. And if I change a little bit a step response, I get something very similar as before. So quite sharp, even if the gain is smaller. And then I can also look at the signal to noise ratio. So this signal to noise ratio is going to be, of course, a little bit higher because of what I mentioned just before. And this is what we observe here. So we, by the way, don't have the same CPD. Well, we are in a different location, but also because the contribution from the two different way of measuring with a slightly different contribution to the overall force. So that gives us a certain offset. And the standard deviation is also bigger, so almost 3 times, which is the difference in gain sensitivity. So now we are ready to move on to some more image conditions. So let's arm the DAC again, so that it will trigger whenever there is a first trigger coming from the scan engine. So now if you just continue some imaging here, so we see that we have some, so we again have the CPD that is displayed here. So we see similar type of pattern, but we also see some increased noise and in this case some less resolution overall. So clearly this mode is probably less optimized for this type of cantilever, for this type of sample, at least in this configuration. But the nice thing is that it was very easy, very simple to switch between AM and FM on the fly, so depending on what we want to compare. And so for the sake of comparison, we can actually do that quite nicely from fully finished images. So if I go to the DAC, I can actually reload some finished pictures that we have recorded before. So let's say this one here. So directly to the history, sorry. So it's just a simple drag and drop. It can have several files internally. Here I only had 2 because I just wanted to compare these 2 modes. And when I go to this, so yeah, I also have to do 2 seconds. At that time, it was measured over a longer period. If I go full scale, and yeah, and we focus only on this guy. So this was 2 seconds. And yeah, so here we go. So here you see that you have the 2 traces over the same image. We can actually look at them over a different line in the image. What is important to notice is that in this upper area, we had 1 volt applied to the gold electrode, the aluminum electrode being on ground on the sample, and in this lower part, there were no voltage applied. So let's go to this full scale and so make some comparison. So first of all, we can compare, let's say, the overall change when you apply 1 volt when we are in AM mode. So this would be the gold strip before we apply 1 volt and after. So we see that we now measure a difference of almost 900 millivolts. And if you do the same for the heterodyne, so here this is this electrode, and then I move to a higher value. In this case, I measure closer to 1 volt, which is exactly what I have measured. So in this case, it's a bit more quantitative, because when I apply 1 volt bias, I measure this with this mode. Another important thing that we can notice from this graph is that if we look now at the baseline here, so if we sit on the aluminum electrode instead, so on this one, there were no bias neither before or after, because this is grounded. So we see that there is actually a slight offset in this mode, so of about 100 millivolts. So between, let's say, this and here. So when I'm here and here, which we should not see, because this is just grounded, so the CPD should be exactly the same all the time. But it just shows that there is some small offset coming from the contribution of the cantilever. While if I'm sitting on the heterodyne image and I go through this, then it's always the same. So there is no offset due to other contribution. And so if there is no bias applied, then there is no CPD measured. Now we see that there's also a slight offset between AM and FM. So that's the most obvious one actually. And so this is more like how the force is built up. So now to conclude, let's go back to the presentation. Okay, so back to the presentation. So this is the last slide for this first part of the webinar. So my goal was to show how to optimize the overall process, focusing on the electrostatic feedback loop. So with the MFLI, and with an overview of different KPFM mode, and concretely on this AM and KPFM, and also switching on the fly. I think it was quite nice to be able to show on the same image the 2 different values. At the same time, since we could apply a bias to the sample, so we could quantitatively measure the offset of this 1 volt DC. And so for this, we could find out that at least heterodyne was more quantitative. Even though I agree that the image resolution was not fully satisfying, and maybe we'll need another webinar on that topic. But at least it was more quantitative. And so, yeah. And clearly the AM-KPFM mode is definitely easier to set up and more stable, and easier to operate, as you could see. So I think that we already covered quite a lot of information, but mostly from a frequency standpoint. So let's look at the other side of the mirror in the time domain. And for this, we need a faster instrument with better control of delays and with higher sampling resolution, so that we can start looking at some time-dependent phenomena. So Mehdi is definitely the expert on this, so I'm very happy to let him continue the show. So Mehdi, when you're ready.
Thank you very much, Roman, for this nice presentation and also the AFM demonstration. Hello, everyone. I'm Mehdi, and welcome to the second part of this webinar, which will be, by the way, shorter than the first part. So here we focus on the time-resolved method for AFM applications. First, let's see why we need time-resolved methods. So far, you know that scanning microscopy actually provides a high spatial resolution by measuring the system in the steady state in frequency domain. But what happens if you want to measure the transient state of a system? So in that case, we need high temporal resolution, and that is where time-resolved can provide such resolution. One typical example or one typical approach for time-resolved is the palm probe technique. So let's see how it works. We have a decay curve of a sample versus time, and we would like to measure this. To do so, in the palm probe technique, we apply a pump signal to excite the sample, and after a certain time, we measure with a probe pulse. We continue this measurement by sweeping the delay between the pump and probe, and at the end, we obtain the entire response of the system. So to be able to do that in electrical domain, we have to use at least a 2-channel AWG to generate such pulses, and also to be able to sweep a delay in between. And to measure the signal, we need to use a lock-in amplifier because the signals are very weak. We are talking about atomic scales. And so we need to use a lock-in amplifier. But to enable the lock-in detection, we should have a modulation on top of the probe or pump, and this can be done by the AWG as well. At the end, the entire measurement, both signal generation and signal detection, should be fully synchronized. So let's see one example of a palm probe approach. So here we have a KPFM system, and there is a palm probe method integrated with this. For details of this experiment, you can look at this nice paper from the group of Lukas Eng from Germany. And what they did actually, they want to measure the temporal response of an organic field effect transistor when switching on and off the sample. So they measure actually the surface potential versus time when they switch on and off the sample, and by measuring this, they can model it with some circuit elements. But how to do the measurement? Let's look at the setup here. In the middle, you see actually a KPFM system, a deflection measurement, PLL, lock-in amplifiers, and also loop back to feedback loop to compensate the CPD. So, but in addition to this KPFM system, you have a pump signal applied to the sample with a square pulse, and also a probe to the tip, which is a short signal with low duty cycle and also modulated to be able to use a lock-in detection. And in the frequency domain, you have the resonance frequency of the cantilever added with the modulation frequency of the probe signal. So at the end, we need to measure this summation frequency component. That's why they are using 2 lock-in amplifiers. But with our instruments, you can even use 1 lock-in measurement directly at this sideband frequency. So to first look at the signals that we need to use, this blue one shows actually the pump pulse, which is a square pulse, and the green one shows the probe pulse. The width of the probe actually determines how much resolution you have in the time. And as it sweeps with respect to the probe, you can obtain the entire temporal response of a sample. If you zoom out of this signal, you will see that there is also a modulation on top of the probe to enable lock-in detection. Let's have a quick look at this amplitude modulation that we have. So the point here is that you generate a waveform, and then you also generate some sine signals, and then you multiply these two together to have an amplitude modulation. The benefit here is that you can separately control the parameters of the signal, both signals, the waveforms, and also the carrier. So here you can see, for example, while you are keeping the frequency of modulation fixed, you can change the duty cycle of the signal, or vice versa. You can sweep the frequency of the modulation while you are keeping the width of the pulse or the shape of the waveform fixed. That helps us to tune our system quite efficiently. For the detection part, we use a lock-in amplifier. And why? As I said before, the signals are very noisy and we need a high signal-to-noise ratio. And that's the only way to measure with such a noise level and signal level. What a lock-in amplifier does, it receives your signal at a certain frequency and it provides you with the amplitude and phase of the signal with a dual phase demodulation structure that it has. We also need a sweeper tool to sweep the parameters of our signals like amplitude, phase, delay, or also frequency. And also we need to synchronize both signal generation and detection, which can be done with our control software. So to demonstrate that, we use our high frequency lock-in amplifier, MFLI, which covers a frequency range up to 600 megahertz. It has also a built-in arbitrary waveform generator option that has a sampling rate of 1.8 gigasample per second with 2 output channels. And the entire measurement is controlled by our user interface Lab1 that is based on a data server and web server structure. So now let's switch to the user interface of the device and we will see how it can be done. So here is the user interface. As you can see, that's the lock-in part, and here is an oscilloscope, and here is the AWG. So I just simply wrote some program here, and the sequencer compiles this program and upload it to the device, and we can generate any kind of waveforms within the bandwidth of the signal. So let's run this signal and see what we are seeing. So this is the pump pulse, and after that we generate the probe pulse and we sweep the delay in between within one period of the pulse. But in addition to that, we need also to have a modulation on our signal. So with that, you can use the modulation option of the lock-in amplifier, and you will see that now the probe pulse has also a modulation in addition to the delay that is sweep. So now to do the measurement, we should measure at the repetition rate plus the modulation frequency. And this can be done with our modulation option here that measures at the sidebands, whether it is upper or lower sidebands or both. So with that, we use the sweeper, and the sweeper can control as well also the AWG and the lock-in measurement. So with the sweeper, we start to measuring the phase of the two sidebands, which is proportional to the delay of the between the pulse and probe. As you can see here, as we sweep the delay, the phase difference between the two pulse trains will be measured here in both sidebands. One is positive and the other one is negative. So that's a simple demonstration of this. So let's now again switch back to the measurement, to the presentation here. And in conclusion, I would like to just emphasize that time resolve is used to provide actually high temporal resolution in AFM systems. And especially for KPFM, we can use electrical pump probe because we have conductive samples and we can use electrical properties of that. And to implement a pump probe approach, we need to use AWG and lock-in amplifiers together. And the important point here is that they should be fully synchronized, and this can be done with our UHF-LI lock-in amplifiers because it has both tools inside one box. So with that, I would like to thank you for your attention, and now we can we can see if time allows to answer some of your questions.
Yeah, thank you very much, Mehdi. So that was a very nice recap of the time resolved. So now I believe we have a more complete picture from both sides of the mirror in time and frequency. But clearly, time domain is more complex because of this AWG. Okay, so yeah, so we have some questions, even though we have already run out of the hour. So I'll let you sit for a minute, Mehdi. So I will start from the beginning. So actually, there was a question just related to whether the video is going to be recorded and available later, and that's right. We will send. I forgot to mention that in the beginning. So we will send you a link afterwards, so you can watch it again, because I understand that it is quite a lot of information at once. Then I have another question on the first part. So can it also apply to? So can we also apply KPFM to other companies such as Brücke? And so yes, so that would so that's the idea behind all this stuff. So we demonstrated with nanosurf SPM, but the idea is that if you have the vertical deflection and the bias voltage, that's a very basic minimum, then you can do Kelvin probe on any third-party microscope. And for Brücke, I believe you need some of this signal access module to get this stuff. And then if you also get a shaker and end of line, then it's even better. So let me switch now to a question from Mehdi. So what is the actual ultimate time resolution you can achieve with this from probe method, at least on the AWG?
Yeah, that's a very good question. Actually, the minimum time depends on the minimum width of the pulse that we can generate, and with the current AWG, we can easily achieve a few nanoseconds.
Okay, just a few nanoseconds. Then, okay, so now I have a more technical question. So from Lucas, so how do you CPD value in the different mode? So we have shown two, but there could be more, depend on the cantilever amplitude. So this is definitely a complicated question. And it's true that it would also have been nice to see that the value match a little bit better. So I don't think I have the answer right away. Clearly, if you have a smaller amplitude, as we could saw from the slide, where there was a paper from Tino Wagner, the smaller the amplitude, the higher the resolution and the contribution you get from the apex. So the closer you should be to the real CPD. But I don't have more quantitative, better quantitative argument at this stage. But hopefully we can come back with more questions. Yes, so yeah. What's the effect of the Z limit on FM-KPFM? So I guess that's for me. And I'm not sure exactly what the question meant. So of course, I guess it depends how close you want to be to the surface. And so the electrostatic force is rather long range, so you don't need to be so close to the surface. So you can also be far away. Actually, for tip lift, people can go up to 100 nanometer. But of course, the closer you are to the surface, and we also saw that on the graph, then the higher you get from the contribution. And so there are no limit. Of course, you don't want to be necessarily in the repulsive regime, but the closer the better for the CPD resolution. Yes, so I think that we have went a little bit over the hour already. So we will answer also remaining question by email. So it was very nice of you for tuning in. Thank you very much. So I hope that you got some practical insight, since it was a little bit more practical than usual. And so so feel free to challenge us and continue the discussion offline for your SPM application. Thanks again. Yeah, it was great having you here. Bye.